Hi, hello, I'm Kiran Kumar from Nature of Physics and Art. Welcome to my channel. See, today Gauss law we are going to discuss. Part-wise videos with applications I will upload. Please watch my videos. I'm doing videos that is mains and advanced and NEET level videos. Please watch and like my videos and subscribe my channel and share to your friends also. Okay, see, first electric flux, then Gauss law and Gauss law applications we will discuss step by step. See, in which first I am going to explain to you electric flux. What is the electric flux? Number of electric lines of force passing through the surface and perpendicular to the surface is called electric flux. Simply, number of electric lines of force passing through the surface. This is the surface. S is the surface. This is the surface, and this is also surface. Passing through the surface and perpendicular to the surface. See, like this. For example, this is the board surface, and electric lines like this. Electric lines, nothing but perpendicular to the board. Okay, there is a chance to make an angle. That another condition we can discuss theta. Okay, angle between the electric field and ds bar. ds bar is area of vector. Okay, so now first one is S is the surface area. Okay, and ds is the small element area. Okay, and next one is ds bar area of vector, and ds cap, or we can take n cap, unit vector. These terms we will use. So S is the surface area, and here ds is the small element area, and this is ds bar. ds bar is along the direction of normal to the surface, that is area of the vector. Try to understand step by step, we can discuss. Here electric flux, indicator letter is phi. Electric flux, okay, which is equal to E bar dot A bar for uniform electric field. For what? Uniform electric field. For uniform, okay, electric field. For uniform electric field, electric flux phi E, which is equal to E bar dot A bar, and phi E, which is equal to E into A cos theta. So what is theta here? Theta is the angle between the electric field to the ds bar. So we can take here yes, ds is taken as yes here because of ds we will consider for the non-uniform electric field. Okay, so simply here surface area I am considering. Okay, so we can write here that is S, which is equal to A, that is surface area, and A is the area. There is no much difference. So simply try to understand electric flux is equal to EA cos theta. Here theta is the angle between the electric field and ds bar, or we can write A bar, okay. Theta is the angle between E bar and A bar, so ds bar we can take area A bar. Okay, so electric flux is directly proportional to the E. So electric flux is directly proportional to the flow of electric lines. Electric lines, that is based on the electric field only, and electric flux is directly proportional to the area within the boundary So which electric lines we are considering? Within the boundary only. So these electric lines we are not considering. So here outside the boundary electric lines are we are not considering. Within the boundary only. See, within the boundary only. Okay, so here electric lines increases nothing but electric field intensity also increases nothing but density of flow of electric lines also increases. Here less density, here more density. See, density of electric field, that is phi E directly proportional to the E. And next, electric flux is directly proportional to the area. So already taken area bounded. Okay, and third one is theta, based on the angle between the E and A bar. So electric flux varies by the boundary faces. So nothing but here the surface is making an angle theta. For example, the surface and electric field both are along the same direction. Theta is equal 0 and cos 0 is equal to 1. Again we will get phi E is equal to EA only. Okay, so like this we can discuss about the uniform electric field and electric flux formula phi E which is equal to E bar dot A bar and phi E which is equal to EA cos theta. Theta is the angle between the E bar and the A bar. So this is taken as here A bar. For example, this is A bar. Okay, here also we can take center. This is taken as what is that? A bar. Okay, so it is making certain angle like this. This is A bar. A bar is making an angle theta. Now it is clear only. So that another, that is for non-uniform, that we can discuss. Here also we can take A bar is taken as a ds bar. Already I told you. So different examples and formula and related points also we did. And continuation we can discuss non-uniform electric field. This is uniform only electric field, and non-uniform electric field nothing but electric lines of force change in magnitude and direction from one place to another place. But here electric lines are okay uniform only. Next one is non-uniform, and also units and dimensions we can discuss. It is a scalar quantity because of E bar dot A bar dot product is there. Electric field is a vector, area of vector. Okay, but here dot product is there. That's why electric flux is scalar quantity. Just a second, I will clean the board. And see now continuation non-uniform electric field. See, in non-uniform electric field the basic formula I am using phi E which is equal to E bar dot S bar. Okay, so instead of A surface area I took. For non-uniform electric field that variation is takes place, that's why d phi ds considering. Okay, and integration on both sides we will get phi E which is equal to closed integral E bar dot ds bar. Okay, so this will give the Gauss law, and Gauss law, that is electric flux through any closed surface is equal to 1 by epsilon naught times the net charge enclosed by the surface. This give the Gauss law. Okay, so Gauss law. So we can write here closed integral E bar dot ds bar which is equal to q by epsilon naught, and phi is equal to also q by epsilon naught. Just modifying the equations in different ways. So try to understand, and before going to that we have to discuss SI units of the electric flux. Electric flux SI units, that is electric flux Newton per Coulomb, and meter square is area. Or another units we can write volt per meter square. After this we can write rearranging this equation volt meter, and it is a scalar. It is a scalar quantity. Okay, so this is about the non-uniform electric field, and this is about the uniform electric field. In uniform electric field, phi E is equal to E bar dot A bar, phi E is equal to EA cos theta. In non-uniform electric field, so d phi E, which is equal to E bar dot ds bar, so phi E is equal closed integral E bar dot ds bar, which is equal to Gauss law. Here ds bar, okay, so that is area of vector, E bar is the electric field, so both are making an angle theta. Okay, and continuation here, this is the electric flux. SI units is Newton per Coulomb meter square, that is volt per meter into meter square, that is volt to meter. Okay, these two are the units for the electric flux. It is a scalar quantity. Next we can discuss, just one second. And continuation, see here closed integral E bar dot ds bar, that we can write EDS cos theta, which is equal to Q divided by epsilon naught. Okay, the total electric flux through any closed surface is equal to 1 by epsilon naught times the net charge enclosed by the surface, is called Gauss law. So these are the different forms of the Gauss law equations. And here one more point we have to discuss, and dimensional formula of the electric flux. So dimensional formula is Newton is ml t to the power of minus 2 divided by Coulomb is AT, and this is L square. Okay, so we can write dimensional formula finally, m L cube t to the power of minus 3 a to the power of minus 1, m L to the power of 3 t to the power of minus 3 a to the power of minus 1. Here Q is equal to AT, A is the ampere and T is the seconds. Okay, I is equal Q by T, Q is equal to AT. And last one, that is applications of the Gauss law. So what is the difference between them, Gauss law and electric flux? The total number of electric lines through any closed surface is equal to 1 by epsilon naught times the net charge, that is called Gauss law. So here we are taking, this is the electric flux. Okay, so which is equal to E bar dot ds bar. For the non-uniform electric field, integration on both sides, we will get this equation. This is the total electric flux. That's why this equation represents the Gauss law. Already I gave you proof and definition also. And applications of the Gauss law, first thing, it is applicable for the symmetrical substance. Only Coulomb's law, that is for the point charges and uniform distribution of the point charges and law of superposition of the point charges, only Coulomb's law is applicable. But here Gauss law is applicable for the symmetrical substance, and also Gauss law is useful to find the electric field intensity for the uniform and non-uniform electric charged material with electric field intensity. So then here Coulomb's law only for the point charges simply, and Gauss law is applicable for the symmetrical substance and uniformly electric field intensity, nothing but uniformly positive charged body that produces the uniform electric field intensity that we can find with the help of Gauss law. Okay, so already Coulomb's law we did part 8 videos are released. This is Gauss law, in which also we are doing videos step by step. Thank you. I will continue with the next, that is Gauss law to Coulomb's law. Okay, so one thing we can do in this video only, we can, already time is over 14 minutes, that is lengthy video. In the next video I can do that. Okay, thank you.